Well, in this podcast we're going to discuss the renin-angiotensin mechanism. Now, the renin-angiotensin mechanism is very important to understand if you want to come to grips with the homeostasis of blood pressure. And of course, once you've come to terms with the homeostasis of blood pressure from a physiological point of view, you're then able to go and understand the pathophysiology of altered states of blood pressure, both hypertension and shock, which can cause low blood pressure. But let's start off by thinking about the normal physiology. Now, obviously it is necessary to have ongoing long-term control of blood pressure. Now, short-term control of blood pressure is controlled by baroreceptors. Baroreceptors located in the arch of the aorta and in the carotid sinus, in the internal carotid artery, feeding back to the medulla oblongata of the brain. And the medulla oblongata of the brain can influence the activity of the sympathetic nervous system, increasing or decreasing sympathetic outflow. Increased sympathetic outflow will cause peripheral vasoconstriction, increasing systemic vascular resistance and therefore increasing blood pressure. And increased sympathetic outflow from the medulla will also stimulate heart rate to increase cardiac output. And that happens on a second-by-second basis. That's fast and it's ongoing. But the longer-term control, the main thing that controls blood pressure in the long term, seems to be this renin-angiotensin mechanism. So let's see what's going on here. Well, the blood pressure that goes through the arterial system in the kidneys is monitored. So you've got arterial systemic blood pressure going through the arterial vascular system of the kidney. And then just near the afferent arteriole, we have a group of cells called the juxtaglomerular apparatus. Now, some of the cells of the juxtaglomerular apparatus are in the walls of the ascending limb of the loop of Henle, and others are just next to the glomerulus itself, called the granular cells. So basically, the juxtaglomerular apparatus describes a group of cells which are close to the glomerulus. That's the key thing. Juxta means beside. So there's this group of cells beside the glomerulus. This group of cells just by the afferent arteriole carrying blood into the glomerulus. Now, if the blood pressure in the afferent arteriole in the kidney, just before it goes into the glomerulus, is reduced, if that blood pressure is low, this is detected by these juxtaglomerular cells. And the juxtaglomerular cells respond by producing renin. And this is renin with one N, R-E-N-I-N, as opposed to the renin with two N's, which does something in the stomach that we're not going to do now to milking babies. So it produces renin, R-E-N-I-N. And renin is an enzyme. So when the blood pressure in the afferent arteriole is low, that's detected by the juxtaglomerular cells, and they respond by producing renin. Now, floating around in the plasma, we have a short protein called Angiotensinogen, produced in the liver. And Angiotensinogen is an inactive protein. It just floats around. And renin will act on this inactive Angiotensinogen, and the renin will convert the Angiotensinogen into angiotensin type 1. So the more renin that there is, the more renin that is released by the juxtaglomerular apparatus, by the granular cells in the juxtaglomerular apparatus, the more renin that is released, the more Angiotensinogen, inactive form, will be converted into angiotensin type 1. Now, angiotensin type 1 does two things. It will cause a little bit of peripheral vasoconstriction. It will also increase the amount of aldosterone a little bit that's reduced from the adrenal cortex. It has those effects, but only slightly. But then as the angiotensin type 1 goes through, particularly as it goes through the lungs, the angiotensin type 1 is acted on by another enzyme in the lungs called angiotensin converting enzyme, ACE. And in the lungs, angiotensin converting enzyme will convert angiotensin type 1 into angiotensin type 2. And angiotensin type 2 is a much more active molecule than angiotensin type 1. And angiotensin type 2 is a very potent peripheral vasoconstrictor. It will close down millions, billions of systemic arterioles. It is a vasoconstrictor. And if you close down the arterioles, you're going to increase peripheral resistance. You're going to increase the systemic vascular resistance. And when you cause vasoconstriction, increasing the peripheral resistance, that will increase blood pressure, because blood pressure is equal to cardiac output multiplied by peripheral resistance. So angiotensin type 1 converted by angiotensin converting enzyme in the lungs to angiotensin type 2, and the angiotensin type 2 is a powerful peripheral vasoconstrictor, and that will increase blood pressure. Now, the other thing angiotensin type 2 does is angiotensin type 2 will increase the release of aldosterone. Some people pronounce it aldosterone, it's the same thing, aldosterone or aldosterone. Angiotensin type 2 will increase the release of aldosterone from the adrenal cortex of the suprarenal glands, the adrenal glands. So more aldosterone will be released from the adrenal cortex. Now, what aldosterone will then do is aldosterone will work on the renal tubules, and it will cause increased amounts of sodium reabsorption. So more sodium will be reabsorbed from the renal tubules back into the blood. That will increase the amount of sodium in the blood. If you increase the amount of sodium in the blood, that's going to increase the osmotic potential in the blood. The blood will become more osmotic. If the blood is more osmotic, that will attract more water into the blood. The sodium will attract water, it will retain water. And if there's more water in the circulatory system, that is going to increase overall blood volumes. So the overall blood volume will be increased. Now, if you increase blood volume, that will increase venous return. There'll be more blood going back to the heart. That means there'll be more stretching of the ventricle. The ventricle will contract more powerfully, and that will increase cardiac output. Will actually increase the stroke volume, which will increase cardiac output. So there will be an increased cardiac output. And if cardiac output is increased, blood pressure will also be increased, because blood pressure is equal to the cardiac output multiplied by the total systemic vascular resistance, that is, the peripheral resistance. So angiotensin type 2 will increase blood pressure via those two mechanisms. So we can see that the amount of renin that's produced by the kidney is going to determine the amount of angiotensinogen converted to angiotensin type 1. And if the angiotensin type 1 is there, it will be converted into angiotensin type 2 by the angiotensin converting enzyme. So the amounts of renin released by the kidney appear to be perhaps the main factor in the long-term regulation of blood pressure. Now, let's just carry on thinking about the physiology for a minute. If the blood pressure increases in the afferent arteriole, again, that's going to be detected, and the increase in blood pressure will reduce the amount of renin that the kidneys secrete. If there's a reduced amount of renin secreted by the kidneys, then less angiotensinogen is going to be converted into angiotensin type 1. So that means there will be more angiotensinogen, and the angiotensinogen is inactive. It doesn't cause the effects that the angiotensin does. So less renin secretion will mean more angiotensinogen and less angiotensin type 1. And of course, if there's less angiotensin type 1, there's going to be less converted into type 2. So let's relate this to chronic hypertension now, which of course is a very common health problem. One of the causes of this perhaps the main cause of the primary hypertension, is that the kidneys are somehow set to secrete too much renin. And at the moment we don't seem to have any pharmacological preparations that will reduce renin secretion from the kidney. But what we do have is a very potent, useful group of drugs called angiotensin converting enzyme inhibitors. And these work by inhibiting the activity of the angiotensin converting enzyme. If that enzyme is inhibited, it means that angiotensin type 1, which is partly physiologically active, but not very physiologically active, remember. It means that less angiotensin type 1 will be converted into the angiotensin type 2. And it's the angiotensin type 2 which is the powerful peripheral vasoconstrictor and the stimulator of aldosterone release. So the ACE inhibitors can control blood pressure by preventing the conversion of angiotensin type 1 to angiotensin type 2. And that has a very potent hypotensive effect. And one other application of this is if someone's becoming shocked, if the blood pressure is dropping significantly. As we've said, there will be increased sympathetic output from the medulla oblongata. So in shock, there's a greater production of aldosterone, which of course is going to retain sodium, retain water, and it's an attempted compensation to increase blood volumes. So a little bit complicated, but interesting mechanism with important clinical applications.